Hi everyone, and welcome to another iteration of Math Research Live with me, Charlotte Aten. So today I will finally be taking a look at a paper that was suggested to me about polyhedral products, and I realized that actually I had a calculation that I had done when I was in grad school that was related to polyhedral products, and it turns out that I was thinking that the author of this preprint that is linked in the chat that was suggested to me, I was thinking that was the other Cohen. Hi, yeah, I'm happy to finally be doing this here. Yeah, so I was thinking that the Cohen who was one of the authors one of the authors on this preprint, I was thinking that this must have been. I knew there was another Cohen in topology, and I was thinking it was Ralph Cohen. But what I'm realizing is that actually this is the same Cohen, Fred Cohen, who suggested this to me, and I know, or suggested the problem that I'll talk about to me, and I know that because it turns out that the third author was at the University of Rochester, and so that definitely means that this is the Fred Cohen that I know. So Fr Cohen is Fred Cohen, but there is another Cohen out there somewhere, and I'm not as familiar with his work. Yeah, actually, I just realized. Let me see if I can improve my lighting a little bit here, and then I will be right back. That's better. It's maybe too bright now, but okay. It's brighter anyway. Yeah, so I've actually held off on looking at this until now. I mean, I've had other things to do anyway, but you'll get to have the experience of seeing me go through something that I have a small amount of exposure to, but it's definitely not something I've looked at too much, and I'll, I guess, talk you through my thoughts on looking at a survey paper in an area that I don't have much specific design in at the moment. So I'll maybe talk about that more if you're curious about my process of reading a paper. But I also wanted to mention this thing that I had done. And so here is poorly copied and pasted from an old homework assignment from when I was in Fred Cohen, the third author's algebraic topology class in like 2018 maybe. I had answered this question that he had given as like a bonus question about polyhedral products on our algebraic topology homework. And so I guess the first part of this, and I haven't looked at this except for copying and pasting it. I haven't looked at this since all the way back then either. So for the first part of it here, I was just showing that a certain polyhedral product corresponding to the n chain was actually a closed two manifold. And so then I did that apparently, and then the question was, what is the genus of this thing? And so here I had said that the genus is 1 plus n minus 4 times 2 to the n minus 3, and so maybe I'll like draw a small example, and we can take a look at that together, and then I'll take a look at the survey paper. Yeah, I remember that Fred had given this as a problem, just like a bonus problem on the homework, and in this class. It was like the first year algebraic topology course at the University of Rochester, and just because it was related, because it's what he did. He had asked this question, and I remember, I think in class when he had asked it, I was like well, if it's, if it's a two-dimensional Riemann, it's a Riemann surface, like, can't you just compute the Euler characteristic just from the complex that you have? Just compute the Euler characteristic, and then you can use that to compute the genus, right? Because we know how those things are related. And so I did this, and so I did this, and then I told them, that I had done it, and I remember being like, oh, has anyone done this before, or like, I don't know, something along those lines. He was like, no, like, I don't think anyone's computed this before, like, that's, that's good, or whatever. I mean, he didn't say it was publishable or anything, but like, I felt cool that maybe no one had actually computed this thing before, and that was a good early experience for me to have. I had a couple such experiences with Fred where he gave some nice bonus problem for the homework, and I did it and then talked with him about it, and it was a positive experience in my mathematical development. So maybe I'll talk through this and like draw a small example. It's got kind of squished here when I copied it in. I like using the pages in this journal program, but I sometimes like run into the end of the page here, and I dislike it. But I don't know. I like having the pages somehow psychologically. It feels good to me. All right. So okay. Well, here it's in order for us to actually see like what the example is. Let's just what did I just do? Oh, I guess I undid making a new page. Okay, so I have my new page. I would like to copy and paste something. Let's see if I can do that. All right. Don't seem to be able to select. Let's see. Select rectangle. This is a rectangle. Nope. Well, apparently that's not allowed. No idea why. Select region, vertical space. What is this gonna do? Oh, I see. It's gonna make vertical space. All right, I don't want that either. Well, apparently I can't select and copy a region, even though I feel like usually I can. What happens if I select this and copy and paste? Then I'll get another one. So what happens if I select this and copy and paste? Nope, you just can't copy that. Huh. Alright, well, I guess we're just going to have to awkwardly scroll back up and down since I can't copy and paste this for some reason that I have. I select region. Oh, like this. Oh, that's terrible. Alright. Well, yep, no idea why I can't copy and paste that, but I guess this program does not have everything we would desire, and I don't really care to go into the file that I already closed and copy and paste that again. So we're just going to have to live with it, I guess. That's so weird. This is bothering me so much now. All right, like this. Can I copy? Nope, I just can't. It's like I can't select anything that I previously pasted onto here. It just seems like, it seems so senseless. Like, let's see. Like if I include this, I only get the part that I didn't copy and paste. That's very annoying. All right, well, because like they should have an option, right, where you can either copy and paste. Yeah, it's like so you can like annotate papers or whatever. You can paste or open the paper into the into this program, and then yeah, it's nice that you can, yeah. So like I could save an image of the screen, or I could just go back into open the original PDF with GIMP and then copy. Copy a piece of. All right, fine. I'm going to spend longer talking about it than I am just doing it. All right, fine. Okay. So here, just give me a sec. Bear with me. I'll do the thing that I did before. I'll do it again. This is. It's such a bad design because like yeah, it's great for when you're annotating something. You want to like move your note a little bit or something. But if you're just wanting to copy the actual text that you already copied one time, then like it's very annoying. So all right, fine. So now I have to open the thing with GIMP, copy the piece of text that I want, and then come over here and paste it in. Oh, and now I don't have my new page again. Terrible. All right. Anyway, it's like they should just give you the option. They should just give you the option that you either want to copy everything or you don't want to copy everything. Like that's, like, do I just want to copy my notes or do I want to copy everything that's on the screen at the moment? Like that should be what your choice is. Okay. Well, now we have a copy of this again, and I've complained about it enough. Yeah, I don't know. I don't know. I probably could use the copy and paste function on Linux as well, or the print screen option on Linux as well. Okay, I guess here. Let me try and see what happens. What happens if I do that? I see. So yeah, that opens my screenshot program. If I select an area, I could select this area from the image that I'm already viewing. And then, let's see, copy to clipboard. Oh, well, I guess I should copy something else to be sure that I actually copied the thing that I wanted to. Yeah, this is a similar number of steps, I suppose. I mean, it's similar to just opening the original file in GIMP and yeah, I mean, yeah, okay, I was able to do it that way as well. All right. Hello. Yeah, so okay, so I can do it that way too. Thanks for the suggestion. Yeah, so on Linux, on Linux Mint, you can just hit the print screen button, and it's a similar menu. It's a similar menu where you can copy and paste, whatever selection from the screen. But I don't know. I'm either way. Okay, so it's still annoying that Journal doesn't have a built-in choice that's like, I just want to copy everything. But okay, so I'll draw some small version of this thing, and without telling you the whole general definition. So, well, let's see an example. That's the best way to know. It's the best way to know, know what something is to actually see the example. It's not the definition. So our space here, let's do n equals 3, since that's going to be the smallest possible one that will be nice. Well, okay, actually no, I don't want to do it too degenerate of a case. Okay, so so for n equals 3, what am I doing? Well, okay, so for I equals 0 to n, I have so I have this union. So what's one of these things going to look like? Well, okay, so let's see. So if I have well, I guess if I just write this out for the n equals 3 case, I'm going to have a to the 0 cross my x is the interval. Okay, I'll just actually, why don't I just call that I? feel better about calling that I. The AX notation is like the general polyhedral product notation that people usually use. Okay, so A is 0, cross I. Well, maybe I'll just do cross I, so that gives me I squared, cross A to the, so 3 minus 0 minus 2, so 1. And then I'm going to take the union with A to the 1 cross I squared cross A to the 3 minus 1 minus 2, 0. I feel like there should be, I feel like this index should not go up to n, because if it does, then I'm going up to n minus, or I'm going up to -2 here. So I'm actually not familiar with what the 4 main polytope products are. So I could not tell you. Let's see. If I is n minus 2, then this is going to give me 0. Okay, so this is actually going up to n minus 2, so I should only have 2 terms, I equals 0 and I equals 1. And then, okay, and then we have one last term, which is I cross A to the 1 cross I. Okay. So we have that. And so, all right, so your first question is why this space? What's the deal with this? Yeah, I don't know polytopes well enough to know these products. It's my guess is that it's definitely not, though, because this part of combinatorial topology or homotopy theory or whatever is definitely adjacent enough that like someone would have realized the coincidence if okay, maybe I shouldn't say it's definitely not one of them, but like it's almost certainly not one of them. Yeah, I mean, these things aren't going to be like, you know, well, yeah, I mean, okay, yeah, I mean, it's okay, it's like it's an adjacent type of thing, I guess I'll just say, but like in general, I don't think that thinking of these as polytopes is necessarily like the thing to do. Which means it's probably not any of those, but I don't know for sure because I don't know those products. I'd be interested to know though, or if you have a survey paper, you can send me a survey paper. But okay, so what's the deal with this? Why this thing? Well, so the idea is like what I'm doing here is I have my whole space, which is X, which is the interval from 0 to 1, which is also what I decided to rename I. So that's just the whole interval between 0 and 1, including these endpoints. And I chose a specific subspace, which is just these 2 points, the 0-dimensional sphere. And thank you. Okay, I'm already reading one thing in the stream, so I'm not going to read it right now, but I will definitely make sure to open a copy of that so that I can have it for checking out later, and maybe in a future time I can say something about what the relationship is between these things, if any, or just see what I have to say about it. That's right. Oh yeah, okay. Yeah, Twitch is very unpleasant about this. If you try to click a link in the chat from OBS, then it will just open it in or I guess it's not really Twitch. It's well, I guess I can't say for sure, but in this software using Twitch, If you click a link, it opens it in the thing's own browser by default. And if you try to copy the link well, you can only copy the current address of the interface, and so that's actually pointing to this little like Twitch plugin thing for the chat. So like I'll just probably look at the video of this later and then manually type the expression. Actually, wait, no. If I select, this is so stupid. I'm having a lot of complaints about technology today for some reason. Like I just feel like things are not doing what I want them to do. Okay, now I have a copy of it open in my browser. I had to select and copy it. I couldn't just right click and open it in my browser for whatever unfathomable reason. All right. Well, anyway, I have it now. Thank you. So if I have this pair of spaces, right, this is clearly a subspace of this, then, if I want to, I could look at the product of the ambient space with itself some number of times. So like, for instance, I could like, how do I say this? So here I could consider I cubed, which is actually the cube, right? You can consider I cubed. And so the idea is that we could think about this as actually being like the space of functions from a discrete space whose members are like, say, A, B, and C. And so that's what the whole cube would be. Something like that, right? Like these 3 points. But then we might ask, well, what if we had some kind of simplicial complex whose vertices were A, B, and C? Like maybe this 3 cycle without having the interior. Well, then what we could do is we could think about, okay, well, whenever I have an edge like between A and B, then I'll think about that as corresponding to having a product of 3 things, and the fact that there's an A and B but no C will mean that I should have like all of I in the first spot, all of I in the second spot, but then just whatever the subspace that I was given, which is A, in the third spot. And that's what this is. And then similarly, if I have BC, then it's like, okay, I should have the whole space in the second and third slots, but not in the first slot. And so that should be like that. And indeed, that's what this is. I mean, okay, up to an obvious isomorphism, because A to the 0 is like a single point. And then, okay, something just bugged out on me. And then finally, we have CA as well. And so that's why I had that last term, which was like I cross A cross I. Okay. So actually, now if we go back to what I just said before, actually even this identification this identification that I made before is actually maybe not really the correct way to consider it. Maybe we should. You got a bless you from the chat.
Thanks.
So maybe really we should really think that I cubed is isomorphic to the this power, which is I to the like this like simplex, where this simplex is all subsets of the set ABC, like is in like the abstract simplex determined by ABC. So saying that it was like I mean, okay, like literally, you know, like the space of functions from a discrete space with 3 points to the interval is you know, that's what the cube, you know, that's like what the cube is. But we should think in this polyhedral product framework that really the whole space is like the entire abstract simplex determined by the you know, 3 things, for instance. And so here we're only looking at the subspace that is like the corresponding subspace to this 3 cycle. And so that's why I had said this here. I didn't really give the whole definition of what a polyhedral product was in general, and also this n should have been n minus 2. But this is, you know, this is the natural choice of a subspace corresponding to a 3 cycle in this context. But if you chose what I originally called X to be some other space and A to be some other subspace, you could do an exactly analogous thing and consider a corresponding subspace of the product that was defined in the same way, and just, you know, give it the subspace topology. That's what a polyhedral product is. So for instance, I could just as well say, well, if I put in this 2 cell, I would be making, you know, I'd be making the whole, I'd be just giving you the whole cube, or I could remove an edge, or, you know, whatever. I could do various other things, and it would be a different polyhedral product determined by a different simplicial complex on these 3 elements. Okay, so all right. So now the next question then naturally is okay, but what does this look like then? So we have this 3-dimensional cube, and well, this is going to be I cross I is a square, and this A is it's the 0-dimensional sphere, just 2 points, right? And so if we think about what this looks like, this is going to be like this first thing is going to be square, and then points that look like square, and then in the second coordinate either 0 or 1. Well, that's just like the top and bottom of the cube. And then similarly here, we're going to get 2 other sides of the cube by doing this, and we're going to get 2 different sides of the cube by doing this. So we're not getting the interior of it, but this is, so this polyhedral product, which I think I just called Z, this polyhedral product is just just say it like hollow cube. There, I'll draw my little cube. Okay, so you know, as with the comment before about like what the relationship is with polytopes, like this is a lot nicer than the general. This is a lot nicer than the general case. Like this is, you know, this is a lot nicer than what typically happens. Like it's not just like, oh, okay, so it's clearly some polytope, right? I mean, okay, I guess in the sense that, okay, I guess I'm most used to, I know there's like some abstract combinatorial notion of polytope. Like there are abstract polytopes, but like what I'm most familiar with is like convex polytopes, and so like that are like actually geometrically realized, and so yeah, I mean, in general I think you can just expect, even if you start off with like a nice like simplicial, you know, pair of things, like the line segment and its 2 endpoints, you don't, in general, I don't think you are going to get something that's that nice. You just can expect some kind of simplicial complex maybe, but you know, that's more, I'm pretty sure that's more broad. But again, I'm not as much of a polytope person, although I would like to be one day, perhaps. Okay, so then the question is, okay, well, for this we Oh, well, yeah. I mean, I guess it's abstract polytopes. Their time has arrived. Yeah, you know, it's funny actually. When I was an undergrad, I found this book. Yeah. When I was an undergrad, I found this book. On polytopes, and I wasn't ready to read it, but I wanted to do an independent study. I ended up doing it on something else. This is like my first or second year of undergrad. And then when I was in grad school, I was like, I'm finally gonna really read this book like properly. And then I did read it a little bit, but I didn't actually do enough with it, and so I didn't really retain it very well. It was Grunbaum's book, and one day I would like to actually I would actually like to have more faculty with polytopes, but I do have a couple things that I did from when I read that book a bit, and I can maybe tell you about that sometime. I made a 3D image of a counterexample to something that I thought was pretty cool. Okay, but I'm getting sidetracked. So let me before the entire time has gone by, let me at least show you this calculation that I did when I was in algebraic topology 6 years ago. Okay, so the n equals 3 case is a cube, and so. Well, if we do the n equals 4 case, we'd have a similar subspace. We'd have a similar subspace of the 4-dimensional cube, but it's not just going to be like it's not just going to be the boundary of the 4-dimensional cube. It's going to be something else. Like in particular, it's still going to be a 2-dimensional thing, right? Because if we do this for the 4-dimensional cube, we're going to have like this instead. So we're still going to have like the I squared that is going to give us a square. But now we're going to get 4 squares for each of these terms in the union. So then a squared and I squared, and then finally the one that oh, sorry. Oh, no, I'm right. I was just okay. And then finally, the one that's like kind of like split because we're going back around the other side of the circle. Okay. So oh, I missed an entry. Okay. Well, this is out of order, but whatever. I also need. What do I also need? Oh, no, let's see. I had the first 2 spots, the second and the third spot, third and the fourth spot. No, this is correct. I have 4 terms now instead of 3. That's right. Okay, so I get 4 squares for each of these terms, and somehow sitting inside of the 4-dimensional cube. Okay, so okay, so my claim, well, okay, so in this I claim that this is a closed 2 manifold, and I had some reasoning for saying that. So I said it consists of a bunch of copies of a square. 2 components only intersect along the edge of their respective squares, and so you have to check that the edges are still Euclidean. Okay, we can only have a point on the edge lies in another square if that square is of that form. Okay, all right. I see. Okay. All right. So I think that I can buy this. So this is actually. Oh, okay, but then I have to argue for the corners of the squares. All right, I'm gonna believe this, I guess. Fred believed it before too, I suppose. So this is a closed 2 manifold. In order to now argue that I can use its Euler characteristic to compute its genus. So this relationship here, that the genus is 1 minus 1/2 times the Euler characteristic, it's only true for orientable manifolds. Like, it's only true for orientable surfaces. So like this two-dimensional surface better be orientable, or else this won't work. So we can't have like accidentally made a Mobius band or something. I don't remember if I mentioned, I think I knew this when I used it, and I ended up having some other thing copied and pasted down here. Well, that's life. And I can't erase it either, of course. That's fine. So I need that my surface is orientable. I don't remember if I mentioned it to Fred, but I think I for some reason I vaguely feel like I knew that these were supposed to be orientable, or like it like was known for some other reason that they had to be, or whatever. Which isn't necessarily like inherently obvious. You can have some triangulation or some cubical representation of like a Mobius band or something in higher dimensional space. Like it's certainly possible to do that. So like it's not like, at least as far as I can see at the moment, it's not inherently obvious that these are orientable. But if they are, and I for some reason feel like I knew that they had to be, or was told that they had to be, or something like that, then we can use the Euler characteristic in order to compute the genus, and this is the relationship between them. And so the Euler characteristic, remember, is vertices minus edges plus faces, and I believe it does not matter whether we're using triangulation or using squares or so forth. Yeah, and so actually let me try to convince myself of that again really quick, just to think about that. So if I have the square, then I have so 4 vertices minus 4 edges plus 1 face. So 1 versus if I have the 2 triangles, I'm going to have 4 vertices minus 5 edges plus 2 faces. And so having the extra face makes up for having the 1 more edge. And so even if I did the triangular subdivision, I'd still compute the same quantity. So, if to you the Euler characteristic is definitely the thing associated with the triangulation, it's okay, because even if I subdivided my squarulation into a triangulation, then I would still get the same number. Okay. So I just have to count the numbers of vertices, edges, and faces in the square sense in this thing. That's what I need to do. Okay, so what did I say? Okay, so it has 2 to the n vertices, which I still believe now, because it's the set A to the n. Those are going to be the vertices. And let's see. So yeah, I also believe that, right? Because when n was 3, we got 2 squares. When n was 4, we have a squared. So this 2 squares, 4, right? So we got 2 squares, then we got 4 squares, and then when we have a cubed, we're gonna have 8 squares. So it's 2 to the n minus 2 squares, because when n was 3, we got just 2 squares, and it goes up by a power of 2 each time. So we have that many squares, and each of them gives us 4 edges. Okay, but each edge appears in exactly 2 of the squares, because this is actually a subdivision of a manifold, and so each edge has to just appear in 2 squares. It can't, and it has no boundary, so it can't appear in just 1, and it can't appear in more than 1. Okay, so that means that the total number of edges then is, so the number of squares So that number of squares, but each square has 4 edges. And then we have to divide by 2 because each edge gets counted twice. Oh, and then of course there's n of these little pieces as we go around our n cycle that's defining our polyhedral product. Okay, so that's I believe this is the correct quantity. So that means that just comes out to n times 2 to the n minus 1. Okay. So oh wow, I've never been rated before. Yeah, I know what it, no, Nova's checking if I know what being rated is. Yes, so I have read about this. I hope that it's cool. I hope that it's a really positive experience. Being rated. Hello. I'm close to computing the genus of this polyhedral product. Let me see if I have my picture for the n equals 3 case. So the n equals 3 case is this cube. It's a hollow cube. Hello. I have a cube here for you. I'm trying to compute the genus of the higher dimensional version of this. You can see there's the 4D one. But you don't have to be afraid. It's not really higher dimensional. They're just 2-dimensional complexes. So it's all good. These are my notes from when I was in grad school. Yeah, so I'm close to computing the genus of this. Hello. And yeah, I mean, you can ask me a question if you want. You know, I can definitely answer any question you have. If the question is what are you doing here, then you know you might need to stick around for longer. But like, definitely feel free to hang out or ask about whatever. Yeah, I'm talking about some complexes that are made in a particular way, going over something that I did in grad school. Wow, there is quite a bit going on here. Wow, hype train incoming. This is exciting, chat. This is like pretty awesome. Oh, you know, we have my partner made a 3-hole donut emoji too. Here, let me see. Let me do the emoji. Oh, okay, now it's okay. It's giving me something new that I've never had before here. Let me see. Can I get no? Okay. Well, it's somewhere. Oh no, it's here. That's right. Here maybe. Oh yeah, here it is. There. I do a fair amount of topology here, so there's always lots of donuts and cubes and things. You can see I've got my line segment. Yeah. I'm sure that someone's baked. Oh, yeah. So yeah, this is a donut to a topologist. This is the oldest joke in topology. It's the oldest one that there is. I actually don't know. Let me think about. Okay, well, no. Okay, so let me check actually. Since okay, so I said that for n equals 3, we get this. No, but this isn't going to give us 3 in general, is there? Let's see. So if I do n equals 3, well, I know that actually I should get 0, right? Yeah, because that's going to be 1, and then that's going to give me -1, and so then I'm going to get g equals 0. If I do n equals 4, then I'm going to do 2 times 0. Okay, so g equals 1. N equals 5. So it'll be 2 squared is 4 times 1. 4 is 5. Well, this exact construction can't give us the 3-hole donut, unfortunately, because let me just double check. Because 5 minus 4 is 1, and then 2 to the 2 is 4, so 4 times 1 plus 1 is 5. So we get the sphere for n equals 3, the regular donut for n equals 1, and then we get the 5-hole donut for n equals 5. So unfortunately, we can't make the 3-hole donut with this exact version of the polyhedral product construction. The smallest number of holes in our donut that we can get is 5. So apparently something along the lines of this is the n equals 5 version of this. So this is like a 5-hole donut. That's the next biggest one that we can get. So the 3-hole donut can't work. You know, to a topologist, the donut hole isn't a hole at all. It's just a single point because it's contractible. Also, the donut doesn't really have one hole. It has 2 holes actually in a different. Okay, so in the genus sense, it has 1 hole, but in like the homological sense, the donut has 2 holes because like there's the hole that goes like this way, and there's the hole that goes this way. There's like the one that goes around the middle. That's like the usual donut hole, but the one that goes around the like, it's like a tube, and like it has a hole that goes around the outside as well. Donut points aren't as tasty. Yeah, there's like 2 basic loops. There's like 2 basic loops in a torus. It's like, there's like the one, like, you know. So this is what I was trying to show with my hands. There's the one that goes around the middle like this, but there's another basic one that goes around the outside like this. And if you think about it, you can't really turn either of those into the other one. Like if you took a piece of string, there's a difference between tying a piece of string around the inside of it like this versus tying it around like this. Like they're different. Yeah. So, yeah. Thanks so much, everyone, for checking out my stream. I appreciate the raid. I'm still pretty new to all of this, but I whatever's going on, I appreciate. I guess I open this. Seems awesome. There's lots of stuff going on. Things flying into this anime character's mouth. Seems good. I don't know. Yeah, it seems pretty awesome. Yeah, that's really fantastic. Thank you. I didn't realize it would be so busy today. It's just a lot of stuff going on. Yes, absolutely. Well, yeah. So let's see. I talked about that. Yeah, it would be nice to try to find something with genus 3, so I could know what polyhedral product actually made the donut that is like the emoji that I have. That is the custom emoji, but. The thing is, like, polyhedral.
I'm gonna keep it a secret.
Oh, you know. Oh, my partner claims to know which polyhedral product it is. Yeah. Oh, okay. They might. It's possible. So these things don't have to be closed manifolds in general. Is the thing. So like, if I did, where's my cube one? Like, if I did this, but then I just didn't put in the edge between A and C. That would remove this piece of it, and it would be like instead of being a cube, like a hollow cube, it would just be like the cube, but you would only have, you'd be missing, say, like the top and the bottom. So it would still like, you know, it would still have the sides. It'd be like a box where like you only have the sides, but you removed like the bottom of the box. It's hard for me to draw this, but it's like you only have 4 squares here. There's no top and there's no bottom. You can just, stuff can go right through. Yeah, this is Journal++. I was complaining about it earlier. I like it in general, but I wish that there was an option to like like, so I like had copied this text from some document that I had written in LaTeX like years and years ago, and so I had copied and pasted it into here so that I could mess with it because I didn't want to copy the whole document; it was too much. But then I discovered that like if I select like this thing that I drew, then I can copy it and I can paste it and I can like have another one and like that's fine. But like if I want to copy this again, say I want to have another copy of this, it just doesn't. It just doesn't. Oh, okay. I've just realized something. The reason why it was giving me this behavior that I didn't want. Okay, well, I still don't want that exactly. I want to be able to copy it. But like, I realized I can double click and I can grab these and move them around. So whenever I copy and paste something. Oh, okay. But what if I now hit C on this and then hit V? Oh, I can just copy them. All right. I take away my complaints. I just wasn't familiar enough with this piece of software. Okay, maybe. I guess I would want to be able to slice a piece off of this now, but I'm sure I can do that with the eraser somehow. Okay, so now that I have this, I see. Okay, so now I could have gone back down here and I could have said, okay, now I want to paste this. I could have pasted it in. All right, all of my problems are solved. My crops are watered. I feel transcendent. No, not quite. I still can't erase pieces of this. I want to be able to get rid of pieces of this now, but okay, whatever. Good enough. All right, I'm happy with this. I'm learning so much about Journal++ today. That's my biggest discovery so far is that I can copy and move around the text things that I've previously copied and pasted, or the images that I've previously copied and pasted into here. All right, well, that's good. That's nice. Okay. So at this point, I mostly just at the end reread this thing that I wrote, and this got a little messy down here. Oh, okay, I can just get rid of that. All right. So anyway, I'm pretty much totally convinced that I was right about this, assuming that these things are orientable. Showing that they're orientable is more work. I really feel like I talked to Fred about this when I did this problem for his class when I was in grad school, and he said that they're orientable. I'm pretty sure. But yeah, this will be true again as long as these things are in fact orientable. All right. I guess we all believe me. We all believe that this is the formula. All right. Allegedly, according to Fred at the time, I was the only person that did this when he asked his class this, and I was the only person that was able to compute the genus of these things at the time. Although I'm sure that if anyone ever cared to compute the genus of these things, that it has certainly been done by this point, because that was 6 years ago, and as I mentioned, you just need to do this count because assuming that they're orientable, it's just use the Euler characteristic. Oh, sorry. Oh, that wasn't the formula for G. That was the formula for... No, that was the formula for G. That's right. Okay, because I said, okay, I believe that this is in fact the correct number for the edges, and then I did some arithmetic, which I guess I should double check if I'm being super careful. But, well, let's see. It's 2 to the n minus that, plus n times that. So we have an n minus 2, an n minus 2, and 2n, 4. Okay. So we have negative that. All right. This seems. Let's see. So we have that, and then 1/2. Give me n minus 3. Yeah, I believe this. Oh, wait. Okay, this is 4 minus 2n plus n. So I'm gonna get 4 minus n. So that would be negative n minus 4. Which I did so that minus sign would go away. But then that's n minus 4. Oh, there's a typo in the proof, but this formula is correct. I see. All right, fine. So that was the correct formula, which is good because it gave me the right answer for the one that I knew. Okay. All right, I think I'm satisfied with this. Unless anyone wants to see more about this specific one, I think that I'm good on this, and I'd like to start taking a look at the preprint, which I'm happy to discover. Actually, I I'm happy to discover that that actually the Cohen here is that it is Fred Cohen, who was my topology professor for many years. So actually, is the white on black better, or is this is probably more visible to everyone, right? Does this stand out more on the screen? All right. Well, so I guess I'll say at the outset that so I don't really have much of a specific goal for this. So like what your goal is when you're reading a paper, whether it's a survey article like this one, or if it's just on some specific thing, you know, solving some problem, introducing some new idea. It really depends on what you want to get out of the paper as far as how you read it. So I'll fully admit that I have like, I don't know if the right word is like obsessive or particular or whatever, but I feel like a compulsion to read every single book and paper that I'm interested in, like word for word, like in order. And I still try to do that from time to time, but it's really not the best way to read a paper. I just feel like the need to like completely consume all of the information about the thing that I'm interested in like a linear fashion. But like I know like rationally that that's not like actually the most productive way to consume this information. And so if I'm just casually reading like more for like fun or like general enrichment, then I really will just go word for word. And I'll even admit to you, I'll actually go along here and it's like the archive identifier. I'll read all of the individual numbers and everything. I'll read all of this. I'll read like the ISBN numbers on books and stuff, like all of the copyright information. It's terrible, but I feel like I have to do it or it won't be complete. But anyway, I read like tables of contents and indices and stuff like that too, like completely. One time when I was like 10 years old, I read an entire dictionary. It wasn't like the biggest dictionary in the world, but it was like a legit dictionary, and I read the entire dictionary like in order. It was, I don't know. Anyway, don't do that. Of course, I can't remember the vast majority of it, obviously. So if my goal is like just to get introduced to the area, I guess, which I suppose is like about as much of a goal as I have here, then I'm definitely going to skim. So probably like if I hadn't been suggested this paper and I was just searching for stuff online. I missed this comment that you like the black version better. All right, well, the most vocal person gets their way. So here's the black and white version. So, like, if I just found this and I hadn't been recommended it, I'd probably read the abstract. Okay, in this case, I already know what a polyhedral product is. I've heard the words moment-angle complex before. Oh, one of Fred's students defended his dissertation while I was still in grad school, and I attended I think it was his thesis defense. Maybe it was his oral exam. No, it was his oral exam. I attended his oral exam. And so I also remember him mentioning moment-angle complexes. Somehow I am skeptical that he actually ended up... who knows? I don't know what people are doing in finance, but I think that he ended up at Goldman Sachs after this, so I'm not sure if he actually used polyhedral products to do anything in his employment, but it seemed like a cool project. But I have heard these words before, and I've also heard the words toric topology before. And I feel like someone once tried to explain to me what it was in the hallway in Rochester, but I don't remember. So I also have some general idea of what symplectic geometry is about, and strangely, I know what a symplectic algebra is, but don't actually really know much about the geometric motivation. So I'm in a good place to vaguely understand some of these things and hopefully know them better than I have before. It says it's expanding rapidly, so these people are pretty excited about this. And this guy was a great influence to me, and I thought he was super cool, so it should be a good time. Let's see. So this is going to be homotopy theory, but it's a little more combinatorial, which I like. And so things are getting far removed from their origin. That means that things are going well and they're advancing their agenda. It seems like it's good. And so this is going to give us a historical overview, main results. Okay, so now So now, I mean, you know, again, we don't have to and shouldn't necessarily read this in order. So like, since I have some vague idea of like what these things are about, I could see like the history of it a little bit. Whatever the motivation for the moment angle complex is. Okay, it's the intersection of some kind of algebraic surfaces or something like that. They have their cohomology, exponentiation property. Okay, so like, I suppose that I can start there, but if something else like seems more appealing to me for some reason, then like I could go with that instead. So I think that although I've never really, even though I have used homological algebra extensively in my PhD thesis, I've never had to actually compute a spectral sequence before. But I know that will be more of a thing in my life soon, I'm pretty sure. So I am kind of curious what the associated spectral sequence is. So even though I can do things in order, if you really want to see like what I would do if I was really just reading this to myself, I'd probably say, I really should become more familiar with this. Here's an application. What is it? Okay, so if I know what some stable splitting theorem is, okay, I think maybe this is supposed to be the stable splitting from theorem 8.6. Okay, well, anyway, okay, so the cohomology of a polyhedral product has some kind of product structure that's induced by the right adjoint to some splitting. Okay, so let's see. Consequences of suspending the diagonal. All right. So let's see. So this is let's see. Now I think I do need some more notation. So maybe let me skim over this and let me go back to see like where I actually need to understand the notation for what this is, for instance. So this looks like it should be the pair of spaces, the space X and its subspace A, and so but I need to well, okay, so I guess this is the definition, so I need to know oh, they're missing a parenthesis. They're still missing a parentheses. It's okay. It's been published. It's fine. But I need to know what exactly this is. What this is. So I'm missing some pieces to know what this is the sum of the cohomology of. So okay, there's some partial diagonals that make some diagram commute. And then this is defining a product of two cohomology classes of different degrees by taking whatever this partial diagonal thing is and passing in the tensor of these two things. This looks like it's supposed to be, it's somewhat similar to the definition, like the simplicial definition of like what the cup product is. So I mean we have to check the details, but like this is at least plausible that this is some kind of product. Okay, I see. All right, so yeah, I need to know what they're actually looking at the structure of better though. So like I recognize this, but I don't yet. Okay, I guess my goal was to skim through until I saw let me see. Okay, so this spectral sequence is going to help us to compute the cohomology groups of the polyhedral product. There's different methods here. Okay, this is some property that this has. Okay. Okay. All right. So they are actually able to compute a lot of specific examples, which is nice. Okay, and then they have a different geometric approach. Okay. So I'm not sure like how similar like this calculation is to the specific type of thing that I had in mind that might involve spectral sequences, but now that I've seen at least the general types of things that they're able to compute, I need to actually know more detail about what this is in relation to the polyhedral product construction that I'm already aware of. So now I might go back. Oh, and feel free to ask me whatever. This is just like the type of process that I would go through if I'm just casually reading something where I'd like, okay, if I'm really casual, I would literally just start with every single word, and I would just, if I couldn't like follow something through completely in my head, I would just take it on faith that they were correct. Like, depending on how interested I was, if I noticed something that blatantly seemed like either wrong or like I really wanted to understand, then maybe I would compute it. But otherwise, I just kind of let it wash over me to see what the general deal was. But if I was trying to like be a little bit more, careful with my time, I wasn't just totally relaxed and like I was trying to see like what do I really want to get out of this, this is the kind of way that I'd proceed. Where I'd like go through something where it's like, I vaguely know that this might be related to something that I'm interested in. I'll skim through it, be like, I don't know enough detail. Do I care to know more or do I want to bail on it? And then if I care to know more, then I'll go back and say, okay, well now let me go back to where some of the definitions of these things are given and see if I can start to get a better idea of what's going on with the notation and stuff. But like, I really will just try to skip into like later parts of the thing without reading everything first. Especially because like there's always motivation for giving a lot of background. This is a survey paper. It'll spend a long time telling me about, various historical things, references, things that I don't need to know necessarily in order to just know like what the basic thing is. Okay. So, all right, well, okay, so these are just a bunch of specific applications. I see. Okay. Well, that's nice. Okay. Yeah. Okay, so K is just some simplicial complex. Okay, so this Z of K x A, this is the polyhedral product that I'm familiar with. This is the big space X. This is its subspace A. This K is what was the cycle before, the n cycle before. This X was what was the interval before, and this A was the thing that was the 2 points before. And so for each simplicial complex K, there is a functor that is taking us into okay, so I guess it would be from pairs of spaces into top, but they're saying C of M whose objects are pairs. Oh, okay, so this is slightly more general. I see. So this is slightly more general than what I presented before, because they're saying this C of M, it's a sequence of CW pairs. So I said something slightly different, which was just a pair of topological spaces, but theirs is more specific in the sense that they're saying, okay, well, let's only consider CW complexes. They're also saying that they should be based, but that's just like, you want to do homotopy, you have to choose a base point. And okay, I mean, I guess you can get into like, you don't really have to, and Grothendieck said it was bad and you should just think of the groupoid instead or something, but let's not go there. So they're saying here, okay, well, you could really, for each component, for each like coordinate, you could choose a different pair of spaces if you want to, or CW complexes, whatever. I mean, like that's fine. So just at first, just to make it easier for ourselves, you can always just think that each of these pairs is actually the same pair XA, right? But okay, you could play the same game with them being different pairs of spaces too. All right, and so then there's some functor that is given as the colimit of a diagram where for each face. So okay, so K is being viewed as a poset here. So the morphisms here are inclusions, I believe. And so they're telling us how to stick the faces into the other bigger faces. And so for each simplex, we're going to have the product of these things where, if your thing isn't, it's what I said before, right? Like if your point, your element, whatever I is, this is like what I was calling A, B, and C before in my first example. If that's in the simplex, then use the whole space. Otherwise, just use the subspace. So you have each of these d of sigmas. Those were the individual things in the union that I was talking about before. These d of sigmas were like my, that was my, like each of these individual terms. Like that's a d of sigma, that's a d of sigma, that's a d of sigma. Where the sigma for each one would be like the one of the things in the simplex. Or like here, I said this is A, B here. This is D of that face that contains A and B. This is D of that face that contains B and C, and so forth. And so, okay, so then just take the union. They're all subspaces of the same space, so you can take the union. You can take the colimit of those things. All right, it says the full colimit structure is used heavily in the development, but okay, it's just the union in the cases that we are maybe hearing about here. And so let's see. So if sigma is a face that's contained in tau, then d of sigma is contained in d of tau. If K is a simplex, then this is just the product. That's what I said before. Okay. Okay, so this is one thing that I wanted to know back when I was looking at the section on cohomology, which is what is the Z hat? And so this is called the smash polyhedral product. Oh, okay, so we replace the Cartesian product. We replace the Cartesian product with the smash product. Okay, so it's the exact same definition, but you do the smash product of spaces instead, which is nicer for. So I've never had any like practical reason in my life that I can recall at the moment, at least, to like in my research to use the smash product of spaces, but I'm sure if I keep going more in the homotopy direction that I will experience it more, and here it is happening. Well, okay, but you can do the same thing with the smash product construction instead of the Cartesian product of spaces. Okay, and it's just the same kind of deal. All right. So now, like, I could go on and look at like where like moment angle complexes came from and all of this type of business. But now that I know that that's supposed to be the smash product version of the polyhedral product, then I see that this definition is saying okay, so I still don't really know what this is summing over precisely, although I'm thinking it has something to do with that we're only looking at certain coordinates at a time, like some subset of the possible coordinates that we have for the elements of for the vertices of our simplicial complex. Okay, so like my guess before seeing the definition is that this K sub I is our original complex that we were using K, but then it's going to be like the induced complex only on the coordinates I, in the set I of coordinates from the possible ones that we had, something like that. And so then this also will be the corresponding sequence of pairs of spaces, but only for those ones that are in those coordinates or something. I think it's going to be something like that. That's my guess. And I can see if I'm correct by going and checking after this. So, okay, but I know that this now is actually not the polyhedral product that I know, but it's like the homotopy version of it where it's smash product instead of Cartesian product. And so then this is just the Q. This is just the Q like cohomology of the space in the usual sense. Okay, and then this thing carries some kind of algebraic structure that's nice, and so. Oh, okay, and so this is why it's good, because now, like, at this point I'm thinking, like, but why do I care? Like, maybe I like the thing that we were looking at before that is making actual shape that I know what it is, like some kind of, you know, some kind of surface that's made up of squares that has some genus that I computed, again assuming that they are in fact orientable. Like, why do I want to know about this homotopy version of this thing? But what they're telling us here is that the curly H thing, this cohomology, this ring, is actually isomorphic to the cohomology of the actual polyhedral product with the Cartesian product definition. That's the one that I showed you an example of earlier, like the one that I was looking at before. It's that somehow, instead of computing its cohomology directly, somehow it's easier to compute the cohomology of this associated thing, which is made using the smash product instead, and that this theorem is saying that you actually get an isomorphism, which is defined as the sum of these maps that we can get. So the point is that studying the cohomology of this homotopy version of this thing somehow is better, in the sense that it's easier to compute it, and you can show that this is actually the cohomology of the original thing. So like that's good. That's cool. That's what I would like to know. I mean, if you just give me a space in general, like what's the thing that I want to know about it? I want to know what the structure of its cohomology ring is. And so this is helpful in that sense, because presumably, right, these formulas are something that I can actually compute in specific cases. Okay, now that I understand that, let's see. I think that they're basically gonna okay. Yeah, so now they're able to actually like deduce properties of the cohomology rings for like specific kinds of examples, and say like, okay, if this is the structure of the simplicial complex, then you can say whatever thing. So like if these pairs are like suspension pairs, like I guess like a space and then a space sitting inside of its suspension or something like that, then you know, like this is the suspension, I guess, and this is the original space. Then like if the intersection of two of the faces in the simplicial complex K, their intersection is 0, then corresponding cohomology classes have product 0. Oh yeah, it is faces. This is definitely like the local, somehow like the induced structure, like the localization of K to J and K to L. That's got to be what it is. Yeah. So okay, so they can actually now use this to say things about the cohomology of like the actual. Okay, well, the cohomology of the actual space. So I guess what's not clear from just looking at this, because like I don't understand, like I don't have an intuitive understanding of what this isomorphism is actually doing on individual cohomology classes, but like I mean in the sense that we know that there's an isomorphism between well, like these individual guys, right, are part of the sum of these guys is what gives you the Qth cohomology of this. So like in the sense that we have established that the cohomology ring of the the smash product one and the cohomology of the original flavor one are the same thing, are isomorphic, then we can say, okay, we know when like this product of cohomology classes is trivial. Let's see. Okay. All right, yeah, so, okay, so, and then there's another class of examples that we can look at. Let's see. Okay. So this is where the spectral sequence calculation originally appeared, is in whatever they're citing here. And okay, so we have some condition on the homology of this sequence of pairs of spaces. All right, I don't want to get bogged down in details. I want to see what the big point is before going to try to consume the details, only if I really need to consume them. All right, so if your sequence of spaces has this nice condition, then there is some decomposition of this. Okay, this is the reduced homology of the smash product version of the space, and you can view it as a sum of these tensor products, which are what? So let's see. This e to the j okay. If this long exact sequence satisfies the condition that there exists isomorphisms for some graded modules. Okay. Oh, e to the j is this tensor product of those components. Okay. All right. So okay. So so this is saying something like if the homology of the sequence of pairs of spaces satisfies some property which includes that it's reduced, or if the cohomology, well, it's saying the homology is said to be strongly free, but okay, but this is cohomology. All of this is about cohomology. So if the cohomology of these ones decomposes in this way, and these ones decomposes in this way, and these ones decomposes in this way, then we get some formula that, well, it's going to somehow involve, again, like looking at what the complex has to do with like specific sets of points from or vertices from the complex, and then also these are going to be these components that are made up somehow from pieces of the cohomology of the individual spaces that it came from. Yeah, so the y's are also, the y's are somehow similarly reflecting like the pieces that came from if your thing was not in the face or was in the face. So, okay. Yeah, so I see something like this and I get some idea of what it's saying, like basically that like the reduced cohomology ring of the smash product version, which, okay, I know is at least the usual, not reduced, but the usual cohomology I know from the previous theorem is actually isomorphic to the cohomology ring of the Cartesian one, which is the one that I care about more from what I know right now. But okay, so this is basically the reduced homology of the Cartesian one, and then, okay, I know I can get some formula that's basically some formula that comes from, I say I know that the cohomology of the spaces in question that the thing was made from, the things that are analogous to like the line segment and the 2 points that I had earlier, if I know that they decompose in some nice way, then I'm able to use that decomposition in order to produce this formula, and that's nice. I mean, I'd have to then have a specific case where I actually wanted to know what this looked like, or if I'm just trying to learn, then like one thing I might do now is say, okay, if my motivation is to like really understand this result or really be able to use this result, oh, well, I'm kind of glad that you found my channel too. thanks for checking it out and watching me read some of this paper. So I do many things. I usually like to say I like combinatorics, category theory, and universal algebra. The first pages give the same examples that your professor gives. Wait, which first? The first pages of this paper. Universal algebra is the study of just general algebraic structures. So it's we can think of maybe the best thing for me to ask is this: if you want to know what universal algebra is, what is your math background? Have you taken calculus, abstract algebra, linear algebra? If you have had high school math but didn't take math beyond that, my answer is going to be a little bit different than if you've had linear algebra. So I guess the simplest answer that applies to everybody would be that universal algebra is the study of ways of combining things that make other things. And so you can think of addition or multiplication as algebra things, but you could also think of like the game rock, paper, scissors as an algebra thing, because two moves are chosen, rock and paper, rock and scissors, whatever, and one winner comes out. So that's like an algebraic operation. So would any number of other things. In some I think in a very real sense, there is no true highest layer of abstraction in math. It's just that at some point, once you have strong enough abstractions, they can all describe each other. You can do category theory in some kind of set theoretic foundation, and so in that sense, you'd say the set theory is more abstract in the sense that the category theory is studying specific things made inside of the set theory. But on the other hand, you could also use category theory to describe notions from set theory. So it's neither one of them is like inherently more abstract than the other one. They're just different types of abstractions. But category theory definitely has that reputation. The difference between universal algebra and category theory is that in universal algebra, you're studying algebraic operations, which you could realize in different categories if you want to. But algebraic structures, as studied in universal algebra, they do form categories, but those categories are very special kinds of categories. They have lots of properties that general categories that people care about, like in topology or in other areas of math, don't have. So for instance, categories of algebras have all products, even like uncountably indexed products. You don't have products of objects in arbitrary categories, but people do care about categories that don't have that, for instance. Or you always have a notion of free objects. Categories of varieties of algebras in the universal algebra sense have a free forgetful adjunction. So you can use some language from category theory to describe these things, but they're much more special than just general categories. And so this is a different it's a different thing, I guess. This is is the simplest thing to say. So you can study models of some notion of algebraic structure in other categories as well. I can have topological versions of group theory, for instance, or ring theory or whatever. Or you can think of categories as being like a kind of partial algebraic structure, and in that sense you might say universal algebra is more general because categories are like a special kind of algebraic structure. There's just it's not really like there's like a strict hierarchy of these things. It's kind of like they just each can describe each other in some way. All right, I'm kind of ranting now, but that's cool. So if you were a statistics major too, you definitely might have been more in the analysis direction. I see. Page 4 was where the examples were given. So I was on page 31. Debbie, do you want to say hi to everybody? Here. Oh, there he is. Dobby. Here, say hello, buddy. Okay, bud.
He wants you to give him a hug.
Oh, okay. All right. Oh.
Aww.
Okay, buddy.
Such a cutie.
Oh, Dobby. Oh, do you know the cohomology of the polyhedral products, bud?
He looks like he wants to get picked up.
Oh, I don't know. Okay, should I try to pick him? Do you want to be picked up, buddy?
Like a baby.
You want to be picked up like a little baby? Oh. All right. Will you tell us about the smash product version of the polyhedral products, bud? Why is it better? Why is it easier to compute the cohomology ring that way? Do you know? So sometimes he does know, but he doesn't want to tell us the answer because he wants to give us the learning experience of figuring it out for ourselves. If we didn't go through the examples ourselves, then we wouldn't learn. Okay, buddy. All right, Dobby. He gets so jealous. I'll have meetings with people and he'll hear the other people and he'll come out and want attention even though he's been so chill just all day. And then he'll need all the attention. Okay, buddy. Okay. All right, I'm going to put you down now. Okay, all right. There you go.
I love it, Dobby.
Who's a good boy?
What do you want?
Nah. All right. He's lost interest now. Okay. So, I was looking at what was on page 4. Oh, no, not this list of examples. The 3-sphere is realized as this. Oh, okay. So you're saying okay. So what was the, these are, the same examples that your professor gave. I see. Okay. I see. So, oh, okay. So I see. So you loved linear algebra and graph theory, and probability was great too. Well, yeah, I think it's a good thing. You don't absolutely, if you know that you really want to go. I mean, okay, master's degree is different from PhD in the sense that, like, if you know you want to do a master's degree, you don't really have that much time to choose if you're going to do like a master's thesis, that kind of thing, because usually it's only a couple years, right? So you really should know at the beginning what you want to do. For PhD, if you're sure that you want to do a PhD, even if you're not sure about industry or academia, which, I mean, just due to the job market, I mean, maybe no one you can really ever be totally sure. And not that it's a completely binary decision either, but you don't have to know at the beginning of the PhD even what research area you really want to be in. But if you do know and you make some good connections and you stick with it, it can be really rewarding to like put in a lot of time and energy into it and like have a good outcome. Like, I had a pretty good idea of what I wanted to do when I went into grad school. And although I did go straight out of undergrad, and I basically did what I set out to do, and it's been fruitful for my career so far. I wanted to be at this particular intersection of areas, and I've basically done that. But yeah, I mean, I'm happy to give advice if you have specific questions. I'm also always happy for people to email me with questions as well. You can find my info out there. Within reason, I will give career advice. So in Rochester, there are, so as far as algebra, there are people who do number theory. So like you definitely have, I don't remember if you did ask this actually. So there are people who do number theory, like Dinesh Tucker. There's also, I guess would Thomas Tucker be number theory? I mean, it's algebra. like arithmetic dynamics is what he does. There's some people who do arithmetic dynamics. Naomi Joknowitz, she has had a grad student before, but I think it's been a long time. But she also does like algebraic number theory. So I don't. Yeah, I mean, so if that's what if you definitely are interested in number theory, then that's a thing that you can do. If you mean like homological algebra, or you want to do like something that's more like in the algebraic topology direction, then Doug Ravenel, I think last I knew, was still taking grad students, and he's he's quite famous in the homotopy world, right? He does like stable homotopy theory, and so definitely he would be a possibility. As you may know, the third author on this survey paper that I'm looking at currently, Fred Cohen, he passed away a few years ago, but he was he did this, for example. Well, you mean like this thing that I'm looking at right now? Am I going to apply this to machine learning? I don't have any particular, as I said at the outset, I mean, I was curious what the spectral sequence calculation that might appear here was, because I saw that in the table of contents, and I thought I might want to compute some spectral sequence that I'm interested in soon. But I mean, to the extent that it's possible, but yeah, I didn't have any specific design for this. It was just that somebody suggested that I take a look at this paper or this preprint, and I was like, oh, actually I had done a calculation of the genus of a family of these polyhedral products before, because Fred Cohen, who is as I now realize, I thought it was the other Cohen, but it's Fred Cohen, who is the one who I know, who is the third author on this survey paper. He had given me this problem to do, or given the whole algebraic topology class I was in this problem to do, and I did it. I think I was the only one who did it, and it was a cool thing. And so I had some background with this, and I'm now just taking more of a look at it. But as far as this paper goes, I don't have really much more of a design than that. I did wonder one thing when I had thought about doing this live stream, which was can you do an analogous thing in other categories? And I think that the answer seems pretty clear that it's yes. I'm not sure how helpful it would be necessarily, but I'm particularly curious about, like, I don't know if I'll do it in this stream, but I'm particularly curious about thinking about what happens if I do this with algebraic structures instead, since I'm a universal algebra person. Because I can take products of structures, I can have pairs of, an algebra and a subalgebra, and yeah, I mean, I suppose, yeah, so I suppose that, let me think about this. Okay, well, I guess doing the thing is mostly just thinking about it. I don't necessarily have to write anything. So now that I'm thinking about it, though, if I had a pair of like a group and a subgroup, and I did the analogous thing, and I looked at the corresponding sub thing of the product, then yeah, I'm not sure that it's obvious that it would give me something interesting. Yeah, actually, maybe it's not really very interesting in general. Well, anyway, oh yeah, so if you're gonna apply to grad school in Rochester, best of luck. I know it's reasonably competitive, and I know that definitely post-pandemic things have been, in general, for applying to grad school, I think not maybe what they were before, Yeah, I hope that it goes well and that you have a cool time. If you do end up in Rochester, there's a non-zero chance that I'll be there at some point. You can say hi and be like, oh, I'm that person from the internet, and I'll be like, oh, cool, you know. But yeah, and I'm sure you'll have a great time wherever you end up. Yeah. Okay. So, oh yeah, I was just checking out these examples, but what was I was looking at something on page 31. I do have algebra things that I've applied to machine learning, but not this yet. I'm still just poking around at this because it's adjacent to things that I'm interested in. All right, so I feel good about having some idea of what the results in this section are talking about. Let's see, where had I wandered over to? Oh, okay. So this is a similar. Okay, so I saw this example. There's a similar family of examples that it's nice. It's another case that is nice. I don't know what C is here. Something that you can make from A, apparently. All right. So these are some similar things. Okay. Oh, now there's a different example. This is like, I find it funny because, like, okay, I know that casually skimming through a paper like this is like, and I mean, to be fair, this is a survey too. It's not like it's supposed to be all original results that are like fully explained or whatever, right? But like it's funny to me because, like, just reading through this, like I mean, I've gotten pretty over being like shy about like doing stuff, even posting stuff on the internet, making mistakes, whatever, because, like, you know, that's how you learn. And also, I'm a professor, I give talks all the time, like I teach classes, and, you know, like you kind of get over it. But still, a part of me feels a little bit shy, you know? And I think, like, oh, you know, am I not getting it fast enough? What if somebody watches this who's, like, really an expert in this exact thing, and they're like, she didn't even say that the way we normally do, like, didn't realize, like, you know, like, what the relationship was with the thing with the Smash product instead of the Cartesian product, or, like, and, like, even if something literally says it's a theorem, like, I feel like it's like, but maybe that should have been more obvious to me. Maybe it is a theorem, but it's, like, not, like, you know, what if it's not really, you know? And it's so funny that, like, it never really goes away. And, like, I don't identify as, like, having imposter syndrome. Like, I don't really feel like that has, like, that has really spoken to me the way that it sounds like it's spoken to that notion is spoken to some other people. But, like, it's funny that, like, it's just the thing that, like, whatever you know, you feel like that's, like, the most basic level of knowledge that anyone could possibly have. And, like, you feel like this emotionally, even though intellectually you know that last year, 2 years ago, you didn't have that level of knowledge, because it includes things that you just learned a few months ago. And so it just feels like it never goes away. Like I just think, like, oh, you know, I can't believe that I'm still not an expert in, like, these 8 different areas of math. And, like, you know, yeah. So, like, it's, you know, I understand. Like, you don't have to. I appreciate you, like, confirming this for me, that I'm probably, like, one of a very small group of people that knows about the thing. But, like, I mean, I do know that intellectually. It's just emotionally knowing that is harder somehow, because, I don't know, it's like speaking a language. Like, once you speak the language, you're like, it's so easy. Like, you just understand it and you don't have to do anything anymore, right? Like, okay, maybe math isn't exactly like that because there's still work, but, like, it's kind of like that, though. Like, emotionally, it's hard to understand that, like I know that other people can't speak English at all. Like, there are people who can't speak English at all. I know that intellectually. But, like, it's hard for me to really grasp psychologically what it's like to not understand English, because I understand English. Yeah, but it's also funny because like I try to be very interdisciplinary. Like I like, you know, I like how, even though I'm not really much of a number theorist, like I like that like in number theory people use ideas from so many different areas, and like I think that's really cool, and like I've you know, I like that kind of that style, you know, because making the connections between the different areas is like what's really interesting, and so I try to do that, but that means that I'm like trying to get to like a really high like expert level of knowledge in like 6 different types of math at the same time at any given time. And like that makes my progress in individual areas like slower, because if I just did one thing like really focused, I would probably progress much faster. But because I spread myself out really thin, it takes me forever to progress compared to people who only do the one thing. And so that also can make me feel a little bit insecure sometimes, I guess, because like I'm like I have this paper that hopefully will be published soon that I've been working on edits for a long time, like explaining things in a lot more detail. That's constructing spaces from n-dimensional or n-area quasi-groups. And like the amount of differential geometry I've done in that paper is like you'll see when I post the new version of it, hopefully within a few months, fingers crossed, hopefully this year or at least next year soon. Is like more differential geometry than I've ever done in my life. But like I'm starting to feel like I actually have some basic understanding of differential geometry after you know, doing this thing that apparently hasn't ever been done before. I recognize the name of the theorem, but I do not remember what the theorem says. All right, I'm curious. Let me find out. I just earlier in the stream remembered how to actually copy and paste things, that I need to copy and paste things from the chat, because I can't click on links for some reason. Oh, this thing. Okay, yeah, so I didn't remember the name of the theorem, but yeah, I'm definitely aware of this. Yeah, I was just on the page. So it's that if the Galois group of a polynomial isn't solvable, then you're not going to be able to solve it by radicals. I remember this. I couldn't give you a good presentation of the result off the top of my head because it's too far from what I actually do day to day. But I do remember that if the Galois group is solvable over the ground field, then that means that it is possible to actually form a sequence of radical extensions that take you up to the splitting field, and that each of those radical extensions is telling you need to include a root of this number that exists in the previous level in order to be able to write down the solutions. So like I do remember the explanation of that, and so yeah, that I feel good about the general idea of that. The actual details of it are something that would be a lot more. Like I'd have to go back and like unravel what that actually said in order to be able to give a good explanation of it. But like that's the trick. Oh, I'm glad that that's a better explanation than the books. Yeah, I mean, it was a really important thing, because like that was one of these first like impossibility like kind of results or conditions that people really understood, you know? Yeah, so, okay, so this question I can answer. So it turns out that there's only a single, like, kind of. I wouldn't necessarily say this is, well, okay. Yeah, there is a universal, okay, I guess I'll say yes, it is a universal algebra question. This exact thing isn't a typical kind of question that's usually asked in universal algebra, but universal algebra has the tools to discuss this type of thing. The reason why it's not something that's like necessarily strictly a universal algebra thing is that the universal algebra perspective is like, well, there is a general way of including a new element that would that would make a new algebraic structure that might break all the nice properties that you liked before, but you can always demand that there exists a new solution. There's some more general, sort of more categorical kind of feeling notion of adjoining a new element to an algebraic structure. That's similar to adjoining an element to a ring. And like you can even demand that there are solutions to things that normally don't have a solution at all, like one time, or like 2 times x equals or what am I trying to say? You can demand things that just are totally not consistent with like the existing system, like that there's like a new solution to x squared plus 1 equals 0 that's like not any of the solutions that we normally have over the complex numbers. That's kind of what I was trying to say. You could like define 1 over 0. You could do various things like this, and in general introducing those things totally breaks whatever properties the algebra has, but then you can always form a quotient of the resulting structure that will give you like whatever properties you ask for, and then the issue is that sometimes that will collapse everything. Like if I demand that 1 over 0 exists, something that behaves like that exists, so like I want a solution to 0 times x equals 1, then I can demand that, but then if I form such a structure that's like the thing that is freely obtained by adjoining a solution to that, then I will get something that's not associative. But if I demand that it's associative, I can quotient out by what that force is, and that like quotienting out is the notion of quotienting out an algebra by a congruence in universal algebra, but that quotient will be trivial. So the question of like, can we add in a solution to some higher degree polynomial? The answer is, well, yeah, I mean, we could always just like force there to exist one. And we know that they all have their solutions over like the real numbers, for instance, right? The complex, well, okay, maybe not real numbers, but complex numbers, right? We know that if we stick in all the stuff, even all the transcendental stuff, then we can always get everything. No, I haven't heard about Beyond Infinity. I have met Eugenia Cheng though. Chung? I'm sorry, now I don't remember how to pronounce her last name. But she was one of the people we had speak at a session at the joint math meetings a couple years ago now. We had a session on applied category theory, and she was one of the speakers for the session. And I think she was one of the ones that people found the most entertaining, actually. Which, okay, maybe that's not surprising because she's got a media presence and everything, like maybe more than some people that are more purely academic, But it was nice. That was a fun time. I enjoyed organizing that. It is a small world. There's only so many people who do all the things. Math is a small world. That's true. If you want to talk about like chemistry or something, like there's way more people who do that. Like math is a very small world compared to science or engineering. Engineering obviously is like, I mean, even if you choose like, electrical engineering or, chemical engineering, whatever, it's huge, math is, it's not too many of us. I've actually looked up the numbers before, and like it varies a lot depending on who you count as a mathematician, but like I think if we're talking about people who actually like produce research actively, like produce new mathematics actively, wherever they happen to be employed, I feel like what I looked at made me think that the number in the whole world wasn't more than like 100,000 or something like that. Like it's not 1 in a million, but like it's like like we're like like 1 in 10,000 or 1 in 100,000 or something like that. Like we're a relatively small segment of humanity. I should check out her book sometime. I'm still determined that even though I'm doing live streaming, I have a Mastodon account where I like post things. I'm trying to be like it's not like, okay, it's not like I'm trying to be like too cool to be popular or anything. Like, I don't want to be popular, but I don't necessarily want to be so accessible that like you really don't need any math background to follow. Like, I'm happy to answer any reasonable questions, but like there's certain things that I want to just be able to say like you just need to know abstract algebra in order to listen to me talk about this. Otherwise, it's just not going to make very much sense. Like, that's like my default mode, you know? Like, I just, you know, I don't necessarily care to, you know, feel like I'm divided between like, oh, what if this is too advanced for my audience? My audience is just the people who have enough math background that this is a thing that they would listen to. Just because, yeah, I don't know. That's the niche that I want to have. Although some people say they do find the sound of my voice to be soothing, and that listening to me talk about this, even though they don't understand it, is actually like a relaxing thing, which I think is nice. I should really invest in a better microphone at some point, but it's just, it's not a financial priority at the moment. Oh yeah, well, I guess it depends on how big your country is. Of course, some, you know, math is much more popular in some countries than others, but yeah, I'm really hopeful that the parts of the world that are still poised to experience population growth during the 21st century will have math become more popular, because otherwise we're going to have a dwindling number of people who conceivably could carry it on, and so you know, we really need to spread that knowledge into the people who are you know, reproducing at a higher rate, so that we can continue to have it be living knowledge. You know, having like a small handful of super privileged people who are the heirs to all living mathematical knowledge is not a good recipe for our society to still know how to do math in general. Yeah, which is also good then that I'm recording myself doing these live streams. You know, in theory, anyone can just watch this. I do not know this person. What is here? Does he have a Wikipedia page? Maybe. So, like, definitely areas of math. Areas of math do sometimes like go out of fashion. Like, that is definitely a thing that happens. Like, okay, so like for instance, point set topology, even though topology is still a big thing, point set topology, like the traditional study of like separation axioms and like, you know, like this just general notion of topological spaces, like what can you prove about spaces in general, it's not something that's really like a thing that people still do anymore. And like that usually happens, so there's a couple ways that an area can kind of die out. And so like it usually happens when things have been done so much that any new results that are left are so difficult that there's not enough for new young people to come in and like mine in order to get new stuff to publish, and like the area kind of goes like, okay, people start saying like, well, it's solved. No one really does that anymore. And I've even heard that about category theory, in the sense that nobody really does like elementary category theory anymore. As in like, what can you prove about categories in general? Or maybe even like, what can you prove about abelian categories in general? The answer is kind of like, well, we pretty much did it as hard as we can. And so people who do category theory or use category theory now, they're either applying it to science, computer science, applying it to other areas of math, I mean, where it's naturally rose anyway, right? Algebraic topology, algebraic geometry, just algebra, like universal algebra, whatever. Or they're, you know, studying things like infinity categories or like other like higher categorical structures. They're not studying like classical, you know, what they will call like one categories, because they think that, you know, their infinity categories are the new categories to them, you know. I'm not that sold on it yet, but I do like the ideas. Like I do think it's interesting. I don't think I want to start calling something other than what I grew up knowing as a category. And by grew up, I mean that I learned when I was in my 20s, because I didn't know what a category was when I was a little kid. Yeah, so even like universal algebra, for instance, like people, there aren't so many people left. A lot of people are retiring or have passed away. And so, there aren't a ton of people left, but it is getting some more interest lately. Let's see, your professor told you don't stay with group theory, learn more stuff, but then in algebraic topology, fundamental group appear. Yeah, so it's just, like, there are people who are still group theorists. Like, that's 100% true. Like, there are people who are still group theorists. And it's important, as far as, like, the pure group theory goes, it's important that there's a living group of people who understand the classification, because, like, that's used to prove other things, and like we really want to know that not only that that's true, but how it's true. And it's a very involved thing to actually know all of the detail of it. So like people who do pure group theory, whether they carry on the classification or not, like understanding the classification of the finite simple groups, or if they're doing something else, it's an important skill set to retain. However, a lot of people now, are doing things like, doing representation theory, which is, very adjacent to just like the classical, group theory stuff, because, you have actions, right? Like that's what you want to think about. It's also, there are also all these connections. And so it's like, if you look into a lot of areas of math now, there's not really a question that you will do some abstract algebra, that you will do some topology, that you will do some analysis. It's just kind of a question of like how much there is of each of the things. And sometimes there's really not much of one, but like usually you have all the things. And there's usually some number theory around somewhere too, for what it's worth. I think differential geometry, as far as I know, is still got a good amount going on. I mean, there's, it seems like a lot of applied interest still, as far as I understand in physics. There's this whole like family of like adjacent things that are like, you got algebraic topology, but there's also differential topology, geometry, and like oftentimes spaces like the spheres, for instance, taking different perspectives as far as like whether you're thinking about it as like something with a smooth structure versus something that's just like a combinatorial thing or just a topological space. Shifting between those different perspectives can give you different information. And so like I think good night, thanks for joining. So I think that you really I think the differential geometry still got a lot going for it. There's group actions or actions of, rings, monoids, semigroups, rings without negation, whatever, like actions of categories in general come up all the time, that's something that you're going to see everywhere. And that's why when you go to grad school or even upper level undergrad, in my opinion, biased by my own life experiences, a good undergraduate math degree is going to require, this is like pure math for sure. This is going to require that you take abstract algebra, you take a topology course, and you take a real analysis course. At least those three. You gotta. Maybe for other people they'll feel like they had a good pure math undergrad degree and it didn't have one of those things, but for me, I wouldn't want to run a program that didn't have those things. You gotta have topology. Now, sometimes those concepts will be included in a longer analysis sequence. Sometimes people's analysis course will have a lot of those ideas in it because you might want to talk about whether your domain is simply connected to integrate over it or something like that. But like it's really something that deserves its own course, especially because a lot of the stuff that like is like the intro sort of like mathematical logic or like that kind of basic experience with like doing the working in first order logic and that kind of stuff, that's usually really well suited to intro topology or abstract algebra. Point set topology, although at Rochester, I know that Doug Ravenel has done some amount of homotopy stuff in the first topology course, just like intuitively. But like, I think the proper thing is to learn point set topology first, because if you don't know that definition of a topological space, your ability to truly understand the homotopy stuff is limited. I don't really believe in just jumping right to that because it's too loose. Like, it's too informal. Abstract algebra really opens up a lot of stuff for you, because once you have the basic abstract algebra, like you're really able to start reading a lot of things that you couldn't read before. I would recommend I really identify as like with the people who are like, I didn't really like analysis so much, or I didn't want to do analysis so much. So like, when I was an undergrad, analysis was definitely my least favorite of like the main courses, right? But still I liked it though. I thought it was cool, analysis is cool. So I think the older, I want to say a couple things. First of all, I knew that this would be a deficiency that I had, and so I made myself, even if it wasn't like necessarily always what I thought like was like the obvious interesting thing to try, I made myself take analysis courses that I didn't have to take in order to make sure that I didn't end up like completely missing this aspect, because I knew that it would be important, and I wouldn't know where it would come up, but that it would, and that's why people had designed the program to be this way. I think one thing that's exciting about it is that the techniques from analysis are often the things that are the I had to do 2 analysis qualifying exams. So real analysis and complex analysis were separate, and the real analysis was like measure theory, Lebesgue integration, this kind of thing. And so I see. So if you didn't have the chance to take it, that's the thing. It's not necessarily your fault. So for my for my undergraduate real analysis course, it was one of Rudin's books, maybe Papa Rudin. I don't remember which one of Rudin's books it was now, but it was one of them. The Rudins, it's a couple, like the Rudins were both mathematicians, and they were both professors at Rochester for many years. So they weren't there when I was an undergrad, but because of that, there was a very strong influence to use the Rudin book, because like that was they were our people, what was I gonna say? Something about analysis. Oh yeah, so I had 2 qualifying exams. Oh yeah, was that the graduate analysis, the real analysis graduate course that I took that had the corresponding prelim. That was Royden Fitzpatrick, and so I remember that Royden had died and Fitzpatrick. I talked about this on the stream before. Royden had died. Fitzpatrick had taken over, finishing the book up, and there are all sorts of mistakes. Like, it's not terribly written as far as the prose or anything, but there are all sorts of mathematical errors in like computations and stuff. And part of learning from the book is learning to figuring out which things are mistakes and which things aren't. I guess to go along with that story, I don't know what's a good measure theory book for an algebra person. I don't know in particular if there's any book that's written as like measure theory for algebra people. Oh, hello again. Okay, well, as far as books being expensive, I mean, if you really want paper, I mean, you've either got to buy it or make your own black market copy of it, I suppose. But you know, if you can just get into working digitally, then like, you know, you really shouldn't be paying for books. I mean, like that's, you know, you don't need to buy books. Yeah, I mean, anyway, you know, ask your friends where to get books on the internet. I don't know if I'll be banished if people post links in the chat, so maybe don't do that, but, you know. So yeah, or, you know, depending on the situation socially, you know, your professor might just like send you a link to send you a PDF file or something, who knows, right? Yeah, I mean, I think, this is the other thing I was going to say. So I feel like I'm a person that, like, algebra and topology have always spoken more to me, like, or seemed like more, you know, what came naturally to me. And that's why I wanted to take so many analysis courses, so that I would get more comfortable with this. And the older I get, like, when I was younger, I felt like, okay, I know this is, like, a different thing. Like, it's different in its style, you know, like computing estimates, you know, decomposing some operator or something like this, you know, like, I mean, there's some algebraic perspectives, but like, it feels like the methods, you know, like things decaying at a certain rate, meaning that you can do something using, like, you know, multipliers to, like, you know, I just, like, their techniques are just different. Like, it feels different, you know? And when I was younger, I thought, okay, if I get really, really good at algebra and topology, I'll understand somehow how, like, this is really just some kind of algebraic thing, or, like, there will be techniques that will take it over. Like, this kind of was, like, this subconscious thing that it was, like, analysis doesn't feel like algebra and topology, but it should. And so if I do enough algebra and topology, I will realize that they can take over, and they can do this part of math. But the older I get, the more I feel like what actually is happening is that, like, just like there was the comment earlier, like, oh, isn't category theory the most abstract kind of math? What I'm realizing is that there's no like one overarching thing, even if we're just talking about algebra or topology. There's not really any one overarching perspective, which is also why I'm hesitant to give away the word category theory to mean like infinity category for like the infinity category people, because like I feel like there's not really a like most privileged perspective. And the older I get, the more I'm realizing that analysis might just not really be able to be handled in the same way as algebra and topology. Like even if you're very sophisticated and clever in your formalisms, you're just going to be reproducing the same methods. I mean, even look at the various ways that people have of doing infinitesimal calculus, right? Like, it's true that formally those are like, you know, maybe doing some ultra product construction, or just doing some, you know, some quotient ring where you make an infinitesimal, something that squares to zero, right? Like, but the actual techniques for proving theorems are still going to be like the same kind of like comparison of like rate of growth or rate of decay, and like it's going to be the same estimates. Like the actual technique is not algebra. I mean, I don't really think either one is inherently more general, because, like, you might feel from your introductory education, like analysis is like, you know, like formal fancy calculus, right? Calculus is real because, like, functions like y equals x cubed are like a real concrete thing. But if you think about it, in many ways, a finite simplicial complex or a finite ring, for instance, are actually much more concrete than something that's actually a bit mysterious, like functions on the real numbers, which include all these real numbers that are uncomputable, undefinable in any, you know, first order system that we come up with. You know, I mean, like, you can't, you need axiom of choice to do all this stuff, and if you do have axiom of choice, then you can produce all these, like, things like the devil's staircase, typical sets are not measurable, like just all of these really pathological things. And, like, if you really look into it, like, in many ways, the real numbers are much less well behaved than, some of these algebraic things.
How is it, buddy?
It's okay, buddy.
I'll check it out.
All right, maybe it's not okay. I don't know.
Where are you going?
But if you think about it, the real numbers really aren't necessarily the nicest thing either.
Back.
Maybe there really is something up. I don't know.
There's literally nothing going on. No one's even playing their car.
There's nothing going
There's
on.
no squirrels. There's no birds. No one's going anywhere. There's literally nothing going on.
Okay, so I guess Dobby really just doesn't like analysis then.
Maybe it's a ghost.
Oh, it's a ghost.
Just
It's a ghost of a departed quantity. But yeah, I mean, in some sense, the finite combinatorial and algebraic stuff is way more real than the real analysis stuff. But I mean, I think it's all legit math. Like it's all a legitimate thing, and I, I'd like to be able to do all the different parts of math. I feel like that's like the natural thing to do, and it does come up. It's not like it never comes up. Like I'm actually I don't know when it'll come out because as I've said, I have a lot of things going on, but I think I'm going to have a new thing that is more analytic. And unlike my older project, which I also would like to revisit at some point since it's not actually published still, but unlike my older project, which was like analytic, but it was like the, enumerative combinatorics, like Fourier transform over finite fields kind of thing, I want to actually I have a specific project that is like more like proper real analysis in mind, and I hope to do that at some point. It's building off of other stuff that I've been up to recently. But you'll have to wait to see what it is. But I've been kicking it around for a while now. Oh, I see. You're a combinatorialist. I don't know if I'm supposed to take anything more from that, but yeah, I like combinatorics. Yeah, I think counting things is super legit, for sure. That's I proved something along those lines in my thesis actually, which is like that like any first order property of a finite structure is actually naturally able to be checked by counting small substructures whose size is determined by the complexity of the formula in question. So I felt good about that. Oh, okay. This is the extreme finitism. The natural numbers are a finite set. Oh, you know what I'd like to talk about sometime? I don't know about this time, since I only have so much time left. But if you look at, a couple of things. Maybe I'll answer the analytic combinatorics question first before mentioning what I'm going to mention. The analytic combinatorics is like, if you look up like extremal combinatorics or enumerative combinatorics, actually somebody mentioned Terry Tao's analysis book earlier in this chat. I mean, both of those areas like are things that he does a lot also. Like that's actually like, I mean, I guess he does lots of things, but that's actually like what he does. And that's like basically that's basically what those areas are. What is this though? I've never actually, I don't recall ever actually having heard of analytic combinatorics as the area, or as an area. Here, let me, I have to copy and paste this. Modern take theory, alright, well, let me see what this is. Maybe this is just what I would call maybe this is just what I would call enumerative combinatorics. Yeah, this is what I or like extramol. This is like what I would call like enumerative or extramol combinatorics. Well, okay, at least as far as I can tell. Yeah. I mean, there's like a few names, I guess, that people give to a similar thing. But yeah, so definitely, like, you know, I mean, if you look at like graph theory, for instance, people often want to study like properties of like random graphs, or like large, you know, like if I just choose like a large set of vertices and random choices of you know, putting edges between them, like with some probability, then like what kinds of structure emerge, or, you know, this type of thing. Oh, okay, so yeah, I see. You know, I have a copy of the generating functionology book, but I have still not become a generating functions person. But I am aware that is definitely a thing. Like I've messed around with generating functions a little bit, but that's like the extent of my experience. I haven't like actually used them to do anything original. Yeah, so there's lots of places, and for what it's worth, there's even places that analysis comes into universal algebra. Like, part of the stimulus for my machine learning stuff was that I realized that there was a theorem in universal algebra, which was actually an earlier result that was very similar to a later result that was proven in the area of machine learning, formally. And like that result in universal algebra uses like a sharp version of Stirling's estimate. Like the argument it's like a probabilistic argument, like it's a probabilistic result, you know, but it's general algebra. So like, yeah. Yeah, so definitely, if I didn't know any analysis, or if I really didn't like analysis, I would be cutting myself off from all of these possible things. Oh, information theory. So when I was a teenager, I at some point found an information theory book. And I've had this information theory book for 20 years. And one day I might read it. And perhaps. Maybe when I get older, maybe if I get tenure or something, then I'll be like, okay, it's finally time to read this information theory book that I found when I was a kid. But it's okay, so it's like I know about things that are adjacent to information theory, and like I know of like some general heuristics about like how much information is contained in, you know, in something. Like I've seen like these heuristics come up before, like that, like, you know, if something doesn't contain enough information, then you shouldn't be able to get something out of it. That's very vague, but and I also, because of my algebra interests, I'm also somewhat adjacent to people who do like coding theory and stuff, but I just haven't gone in that direction. So like my knowledge of information theory is limited. But I mean, I understand like some very like basic ideas. Oh, and then I guess maybe entropy is also a concept that comes up there. And do you want to say hi again, Davi? Are you interested in information theory? Do you like it better than analysis? There might be some analysis involved, but what is it, bud? What is it? Okay, he doesn't know. He doesn't know what it is. But yeah, I mean,
Mommy, why are you whining?
Yeah, why are you whining, buddy?
Come here.
It's okay, Davi.
Come here. I'm gonna see if he has water.
Do you need water, bud? Maybe he's just still upset about the analysis from earlier.
Buddy, come here. Come here.
Go on, Davi. he got to have a bone that had been like in the crock pot until it became soft last night, and it was like a whole bone from a bone broth, and he got to eat the whole bone last night. And so like now he didn't want to eat his dinner last night, and he's been full, I think, since then. He's not wanting to eat anymore. But he seems like he's doing good. I don't think he's sick or anything. Like he loved it, and he seems like he's fine otherwise. But anyway, yeah. So unfortunately, I don't have too much to say about information theory, but I am adjacent in a couple different ways, I think. But yeah, I mean, it seems like a legitimate thing to study. I don't know that much about it. Oh, but entropy, that was the other thing, was that I've seen entropy used before. Oh, it's okay. This is actually, I think over the course of doing these live streams, this is like maybe my 15th one at this point, I've become much more focused than I originally was, and it's okay. I mean, like, this is like a specific amount of time that I've allotted for doing whatever it is that this is. So it's not like you're really taking time away from me, in the sense that, like, if I really had, like, generally speaking, I don't like try to do like I might do some original computation or something on the live stream, but if I have something that's like big and like pressing, like for time, like if I have like a paper that I'm trying to finish up, like occasionally I'll do it on the live stream, or like a grant application or something, then like I will allot different time for that. But like here, like I plan on having digressions and like having side conversations about different things, because like, you know, like, I mean, that's what it's for, right? Like, yeah, like, I can't guarantee, I mean, you know, this is like some kind of glorified, like, office hours or something. I mean, like, I can't guarantee I'll actually get any specific piece of work done, you know? Yeah. What else is going on in this paper? They said that there was another important but tractable case, but I didn't know what the C construction was. I'm sure I will also be going for a walk in the not too distant future. Oh yeah, hello. I am another math person. We are out there doing math. Huh?
The truth is out there.
The truth is out there. My partner and I have been watching the X-Files again. Yeah, I mean, like, that's, I guess I would say, like, if you're doing applied math, then, like, unless you're, okay, if you're doing applied math research, right, which sounds kind of, you know, maybe like it's an oxymoron, but it's not. So like people who do applied math academically, there may be a specific project to which the math is being applied, but they're also usually developing the theory of it, because if the theory was already developed and just the application was needed, usually mathematicians, like applied mathematicians, aren't necessarily doing that as much in academia, because then people are like, okay, but then, you know, I don't know. Like, I mean, I think I'm more towards the pure side than the applied side, so maybe I'm also not the best person to talk about this, but in my experience or my perception, academia definitely means much more. You're developing the mathematical theory that solves the problem that comes up in the applied setting. Now, if you're in industry, like, there are industry research labs, but if you're like really like in industry where you're like doing a specific application, making a specific product, it's much more likely that the theory is substantially developed and that you are actually now applying it to the thing, because you didn't even do anything new. Because like for like in a business setting or in a setting that has like, you know, even if it's not about like making a profit, but just about like solving a real world problem, right? Like if you're trying to do the engineering to design, you know, some bridge system for a city, you know, like that bridge needs to be designed, and it needs to work, and it shouldn't depend on a bunch of newly proven results that you just came up with, right? Like, that's got to be like rock solid. And actually, the only person I've ever met in my life who told me that what they do is design bridges was a grad student who I met years ago at Iowa State University, and she was an applied math grad student, so not even engineering grad student, but applied math. And so for things like that, I think it's much more like, I mean, I don't know whether she went into academia or industry, I don't know, but like for things like that, it's like you're not gonna be reinventing the wheel, I'm sure, you know, like you just want to know that it works and then do it. Yeah. I don't know what I don't really know what having another Newton is supposed to mean exactly. So I think that in terms of the output, like as far as like the quantity of like original theory that people have produced like during the last century, many people have been much more productive than Newton was. I don't know about maybe more productive than Gauss or Euler, or maybe Erdős, but you know, as far as the quantity of stuff, I think definitely there are lots of people who have produced more because they're, you know, they have that background. And if you mean as far as like being like a world-changing thing on people's perspectives, yeah, you can solve P equals NP. As far as being like a, you know, world-changing thing on people's perspectives, you know, I think that there are many people who have done things that are of a comparable kind of level, and it's just that Newton existed at a time when it's not like we had no mathematical progress before the modern era, but it was much slower because there were much fewer people doing it, and like we were much more primitive in some sense, you know. And now that now that we have more of us and we have enough basic background to go off of, it's like exponentially improving, and like there's just tons of stuff. I mean, there's so much that you can't even get as famous, because even if you do something that's like that earth-shattering, there's tons of earth-shattering stuff going on. So it's like, what do you even spend your time looking at? Let's see. Yeah, so there are a few people, like Eugenia Chung was mentioned earlier, or like John Baez also is like a similar category theory person who has some, like, some of his exposition is meant to be like totally popular, but other exposition is kind of meant to be for people with like some math background but who aren't necessarily like research mathematicians. As far as are you talking about Andrew Wiles here maybe? I think that I generally agree with Perelman that Dobby, buddy, there's nothing out there.
No, go timeout.
Go to timeout, buddy.
No Birkin.
Go to timeout.
Go. You got really fiery.
Yeah.
Go timeout.
That's too much, bud.
Oh, actually, I just heard something on the window.
Oh, jeez. Now if we've scolded him and
I think I did.
okay. Is there something out there? Well. Anyway. What would be more challenging? Oh, so the comment I was going to make was that I agree with Gregory Perelman, right? Who solved the who got the credit for solving the Poincare conjecture. That like it's not like any big thing like this. It's unreasonable that any individual person. Hey, Dobby, go to timeout. Go to timeout, bud. You're still in trouble.
It's so weird.
Go to timeout.
There's definitely nothing going on out there. He's so agitated. Go to timeout, Dobby.
Yeah, but like I don't think that it's really reasonable to give a single person credit for any of these things, because like it really doesn't happen. Like even Wiles apparently did work by himself for a long time, but even then, like I mean, there are other people who worked with him to like fix the gap, I think, that was in his proof when he finally had one. and like, it's just at the end of the day, there might be one person who did whatever is considered to be the last step, but like big things like this are not going to really be like one person was like the person who just totally did the thing. Like, it's not reasonable. And that's why Perelman refused the prize, because yeah. So actually, I am adjacent to something that is related to the P versus MP question here, and so maybe I'll mention this briefly, and also I guess I'll mention I don't have any opinion on whether or not I want either of these things to be true or false. I don't have any strong feelings, because I'm not that close to either question, Riemann hypothesis or P versus MP. But like, so there are people who do universal algebra application in what's the biggest thing in universal algebra as far as big open question. There are definitely a number of open questions that are left, especially because the area is not as big as it used to be. And it had that kind of thing, that a similar thing that happened to like point set topology or like elementary category theory, where like some of the problems got to be very hard, and so like that was also discouraging for like having more people, because then it became like, well, there's not enough, people were feeling like there wasn't enough new stuff to prove, so it dried up a little bit for a while. But so we know that if you look at the congruence lattice of an algebraic structure, that it has to be an algebraic. It has to be what's called an algebraic lattice, and it has to be complete. And so a natural question you can ask is like, which finite, or just which lattices that have the appropriate type, that are that type of lattice, which lattices are the congruence lattices of some algebra? And the answer is that they all are. But there's a more interesting question, which is if you have a finite one, if you have a finite lattice that is of the appropriate type. Oh, okay. I think actually finite and algebraic is so if you have a finite lattice, just say that. When is that finite lattice the congruence lattice of a finite algebra? Right? Because it might be that for every finite lattice that you can find an infinite algebra that for which that lattice is the congruence lattice. But maybe it's not possible to find a finite algebra, and it's not known. Yeah, lattice theory. And so it's not known whether or not it's possible for every finite lattice to find a finite algebra that has that as its congruence lattice. And so this is actually reducible. It turns out it's equivalent to a problem in group theory, which is like, I think is every finite lattice, and again, maybe that has some appropriate choice of condition on it that I'm not remembering what the appropriate. Yeah, the ground set is finite. I mean, lattices always have finitely many basic operations in the usual presentation. They have meet and join. So there's just two, and they're finitary, they're binary. And for the algebra should have finite type. So it should be a finite algebra, and that it has a finite amount of elements, and it should have finitely many operations and of finite arity. So like, yeah, you have to have a finite list of finitary operations. But for a given lattice, it could be that the corresponding algebra for one lattice has 1 million operations, and another one has 1 billion, and so forth. So it doesn't have to be that there's a bound, I don't think. Just that there is for each finite lattice a finite algebra with some number of operations that is not an infinite amount. Here, let me see if I can pull up the Wikipedia page for the thing actually. So it's equivalent to a problem in group theory. Okay, I said it correctly, because algebraic lattice just becomes finite lattice in this context. Oh, and so the Wikipedia page even says this is one of the oldest unsolved problems in universal algebra. So this is called the finite lattice representation problem, I guess. And so, as you can also see there, it's equivalent to a problem about groups specifically. It's in like which finite lattices can be an interval in the subgroup lattice of a group. Like that's, or the normal subgroup lattice of a group. Like that's an equivalent problem. It is subgroup lattice. I guess I didn't have to say normal subgroup lattice. I just looked at the Wikipedia page again. It is subgroup lattice. Yeah, so there's a purely group theoretic approach that you could take as well. But yeah, we still don't know. We just do not know, and it's been an old problem. And now to give you an example of another thing in universal algebra that's also an old problem in universal algebra. Let me see. There's a different lattice representation problem. Let's see. So let me see. Okay. This is a different problem that has been solved. Okay. So I'll give you another link. So the congruence lattice problem has been solved, and that was a big open problem. But so this is a different thing about congruence lattices. It's whether every algebraic distributive lattice is isomorphic to the congruence lattice of some other lattice. So the congruence lattice of a lattice has to be distributive. So in order to have some lattice be a congruence lattice of some other lattice, it has to be distributive. And also, by what I said before, the congruence lattice of any algebra has to be algebraic. So if you have a lattice that is like that, the question was, when is it the congruence lattice of another lattice? And I actually don't remember the answer, but I think maybe the answer was no. Now I don't remember. So, there is a counterexample. Okay, so it's not true that every. Okay, this is what it is. It's not true that every distributive lattice is a congruence lattice. There is a counterexample. And Fred Varang found a counterexample using this result in set theory. And so this is like one of these things where like sometimes something that doesn't seem like it has anything to do with set theory whatsoever, like occasionally it'll just come up that like actually there's just some result in set theory that either proves the thing or gives you the counterexample, and like you just if you didn't realize that was the correct perspective, then you just had no hope. There's I think there I don't remember exactly what the result is now, but I remember there's a similar thing with if you want to know whether I'm trying to remember what it is now. There's something in homological algebra that's like if you want to know like whether a given, I want to say it's like whether a given abelian group is projective or not, then like actually like there's some question along these lines that I'm now not remembering what it is, but it's something like this, where the answer turns out to be that the answer will be yes if you have a certain version of set theory, and it will be no if you have another version of set theory. And so it's not like something that's decidable. It's something that depends on like other axioms that you take or whatever. And like I'm now not remembering what the thing is, but there's something along those lines. And the reason why I said it's something like being projective is because it's something that in order to do the calculation, you have to quantify over all groups is the issue. And so when you quantify over all groups, you have to quantify like over free groups generated by any set of generators, and the existence of certain kinds of sets will control like what happens. And so that's basically the idea. I don't remember specifically what that one is. If I think of it before the end of the stream, I'll give you a link to that too, but I'm just not remembering it at the moment. Yeah, this type of thing happens. So anyway, sometimes the problems are just really hard. But the finite lattice representation theorem or representation problem is still open. The congruence lattice problem has been solved, but it was set theory and it's false. There's a counterexample. Yeah. So like there are other directions of current research, both theoretical and applied. So like there are people who study are studying like commutator theory. Which we have like our graduate seminar for the algebra and logic group at Boulder. Our seminar is basically we're just looking at stuff about commutator theory, which is like a generalization of methods involving commutators from like group theory or ring theory to a more general setting in universal algebra. So those techniques can be used to understand the structure of an algebra better. There's also methods from what's called tame congruence theory, where there's a way of inducing subalgebras from an algebra onto subsets of it, even if those subsets aren't subuniverses or aren't like subalgebras inherently, in some sense. And that can tell you a lot of information. So there's some strong results in tame congruence theory for understanding the structure of finite algebras, especially finite algebras. There's people who study there's more applied things. Like there's people who study a lot of stuff about the decision problems. This is what I was going to say before. So there's a connection to something that's adjacent to things I'm interested in, to the P versus NP, in that one of the big results in recent years has been what's called the CSP dichotomy conjecture. Well, it was a conjecture, but it's now been proven. So here, let me give you a link to this. Let me see if I can send you a nice link. Well, maybe there's no Wikipedia page about it. That's nice. What's a good general? I used to have a link to this page that was like, maybe I can still find it. There was a royal road to the CSP dichotomy. Oh, is it still? Oh, okay. All right. Well, anyway, this used to be hosted by MIT, but now it's just on the guy's website or something. But here's a bunch of information about this. That's the royal road to the CSP. Which paper is this one? I just copied and pasted the same thing again. Okay, I feel like I have a legitimate complaint about this aspect of the browser and this software, the streaming software. Okay. Oh yeah, so that's Jukes' proof of the conjecture. So there were two people who proved it basically simultaneously. But again, the story is basically the same thing, where it's that although those two people definitely like really did it, people hadn't had it before. It was a really huge effort of many people in order to produce the framework in which they could prove the result. Oh yeah, we have so many friends today. That's awesome. So in the next few minutes, I am not going to be, because I am still going to finish up at 9. I can't go for 9 my time anyway. I can't go forever. So there's a question about this type of decision problem, which covers most of like these types of decision problems that you would consider in computer science, like graph coloring. There's different kinds of scheduling problems. All of these different types of decision problems can be phrased as, can you find a homomorphism from some relational structure into another relational structure? and usually when they're both finite. And it turns out that you can ask, well, if I have a given target structure, and I say I want to say like I want to understand like is 3 coloring graphs. So a relational structure is some underlying set, some universe, just of your points or whatever, and it has a bunch of basic relations. So a relation is like an n-area relation is a subset of a to the nth power, like the nth Cartesian power of the set. So in other words, it's a set with a bunch of collections of tuples that tell you which things are related to each other in some sense. So like graphs are relational structures, simplicial complexes are relational structures, like ordered sets are relational structures. You can even encode functions by doing like the graph of the function. So like instead of an operation from a squared to a, I can have a collection of triples where it's like a, b, and f of a, b is the third element. So relational structures, and this is like the model theoretic sense of relational structure. This subsumes, in some sense, algebra. But because it's broader, you can't prove results that are as strong. So just like with the category theory thing from earlier, why do you do universal algebra if there's category theory? Well, category theory is too broad. You can't prove all the stuff that you can prove about algebras and for just general categories. And similarly here, well, you can't prove all the stuff about relational structures as you can prove about algebraic structures. So relational structures might be interesting for various reasons, but they're also like more broad, so you're not going to be able to use the same methods. But anyway, you can use universal algebra to understand this problem because it turns out that there is like an algebraic structure that you can associate to a given relational one called its clone of polymorphisms. And it turns out that understanding that clone, which uses techniques from universal algebra, that's exactly what you need to be able to do in order to answer whether the decision problem associated to that structure in this framework is in P or NP. And so like the dichotomy exists there, and that's the theorem, is that if there's a certain type of operation in this polymorphism clone, then it's in one complexity class, and if it doesn't exist, then it's in the other one, and that's it. And so so the methods are really universal algebra. And so so I mean, that was a big thing that was proven like 7 years ago now, I think. And so research goes on in that direction. I've asked people how close they think that like the techniques are to proving proving a result about P versus NP in general. And like people's attitude at the moment is like it's not really like going to be that applicable in the sense that like, and I don't understand this well enough to understand like why this is the case, but the claim is that like you're not going to be able to reduce the general problem down to this class even though it's so big. I don't really know why that is exactly. Like I don't know enough about P versus NP in general to understand that. But like the claim is that although this is like in a similar genre of things, that you're not going to be able to actually prove the whole theorem this way or in this way. But I don't know why. I really don't know why people say that. Like I don't understand it well enough yet to know that. But it is definitely adjacent to the question. And just naively, not knowing any better, I don't know specifically why it's not possible that there is an answer to P versus NP that comes from this direction. I don't know. Another thing I wanted to mention, since we mentioned Tao's analysis book earlier, is also maybe surprisingly, I think Terence Tao has been getting more into universal algebra, which I think is not something that most people would ever have thought would be a thing. We had some interaction on Mastodon last year, I think it was. I think it was I don't remember which summer. It was like the last summer or the summer before. And he's now got some kind of project going on, which I think is along the same lines as what we had talked about back then, which is that he was interested in using like automated theorem proving stuff to like understand which equations, say like for magmas, imply which other equations. And I was at the time was basically like, we've had tools for doing this like for a long time in the universal algebra community, and like the amount of structure that these things have seems to be so huge that it is not feasible to attack it this way because of the combinatorial explosion. Like you can't, you're not going to be able to do that. And then like there are finite structures, like if you're talking about the equations that are true for a finite algebraic structure, like just for a magma, a set with a binary operation, there are magmas that are not finitely based. So like there are structures that there is no finite amount of equations that are true about them that will let you deduce all the other ones just using equational logic. And so because of that, like I said something, you can go back in Mastodon maybe and find the conversation, but because of that I said something along the lines of like, in general you're not going to be able to do this. And I think his response was just like, oh well, let's try to do it for as many as we can, like let's try to do the small ones, whatever, and like that's possible. I don't know. I'm not currently interested in going more in that direction myself, which is why I haven't participated in it, but I get the feeling that if his interest in this is well received, that it might draw more people into the area as well, because he's much more famous and richer than I am and everything, and so I don't know. That'll be interesting, but yeah, I mean, definitely, there's more people who are getting interested in universal algebra again, I think, and who knows? I mean, maybe he knows something that I don't know, and we are going to see some proof of P versus NP coming out from this direction at some point. I really don't know. I think the motivation is just that he's really into the AI theorem proving stuff, and it's a good test case, and like, I mean, I don't think that having a really complete understanding is reasonable, but like, like in the sense that like you're not going to be able to write down a list of, even relatively small, like how all relatively small identities imply other identities or whatever. Like it's going to be that like the combinatorial explosion is too bad. Like having more modern computing resources isn't going to change that significantly, I think, because it's too big. Like the amount of structure that occurs is like, it's like super exponential in how it grows. Like it's just seems unlikely to me that we'll really be able to get a good handle on that through force, even like slightly like sophisticated force, I don't know, but I mean, I hope that they find cool stuff. Like, yeah. So that's really what he's gotten into now, and so like, if you listen to people, like there's lots of people who are into the automated theorem proving and or not just automated theorem proving, but like the formal theorem proving stuff. So I know Cock a little bit. I haven't done Lean yet, but I keep thinking that I will be converted and I want to be converted, but then at the moment I'm still more interested in proving theorems. And I know that there's people who say that they use it to prove theorems, that it's very helpful, or even people saying like I only prove theorems this way. But like, even though it's kind of messy, you've basically seen what it looks like on my live streams, me doing math. That's how I prove theorems. And like, I still feel like I know how to code. I mean, I'm definitely proficient with Python. I know a couple of different languages. I have some experience with these formal theorem proving systems, but I think it's an interesting thing, and I think the math behind some of the formal verification stuff is really cool. I hopefully will have a paper out about that in the not too distant future. But like, I still like doing math like the traditional way. I feel like the progress that I make is faster, because like, I don't know, I can't give a whole rant about this right now, but I feel like it's cool. It's a cool thing that people are doing. I'm glad they're doing it, but I feel like it doesn't feel like it's worth the amount of effort to like formally verify stuff that I'm thinking about. I really feel like just doing it in my head and on paper is like what is working for me. And so yeah, I mean, I feel like I was going to say something else. Oh yeah, so I mean, if you listen to other people talk, like Terrence Tao isn't the only person who talks about this. Universal algebra is a good thing to study if you're interested in automating things, whether it's automating like finding examples or actually like doing formal verification of like verifying proofs, because it's so nice compared to just like the general categories of things that people like to study or like to think about, but it's at the same time something that has a huge amount of structure. And so I've even seen people give talks where they'll say like, you know, if you can't get your formal verification system to easily do universal algebra or to easily do these proofs in universal algebra, then like it's not going to be able to, like the odds that it can do that much are pretty low. Like it's, if you can't do universal algebra, you're not really doing it, you know. But yeah, I don't know who that is, but I'm glad that they're interested. And yeah, I think it's about time for me to call it. Oh, okay. I'm not familiar, but thanks so much, everyone. It was really cool. We got rated. I talked about a bunch of different stuff. Thank you so much for being here and being part of this. I'm glad that I took a look at this and it was cool and I had a good time. And I hope that you have a wonderful day or night or whatever it is, wherever you are in the world, that you just have an awesome time. All right. Until next time. See ya.